Hi, good afternoon. I'm Finlay Scott, so going to be talking about some of the work we've been doing on incorporating the major elements of biological and model uncertainty in stock assessment. And my co-authors are Ernesto Jardim, Colin Miller, and Santi, who's sitting down there. I did have a picture of a fish to start off with, but I had a really bad idea last night that what I was trying to do with this talk was describe how we were taking some of the different ingredients of biological and model uncertainty and then sort of mixing them together and then coming up with sort of a stock assessment cake. But this morning the analogy doesn't seem quite so good, so apologies for that. Okay, stock assessment. Over the last couple of days, there's been a few talks that have sort of criticized some of the current stock assessment practices, particularly around Europe. So I'd like to take the opportunity to also have a bit of a kick at some of the things that are happening. For example, it's pretty obvious that a lot of the uncertainty in the biology is not often considered. So for example, some of the biological parameters that are important, they just have sort of fixed values associated with them. There's no sort of distribution of values. And also the process of the stock assessment at the moment seems to be to sort of gather together a suite of candidate models and then move from that to just pick out one of them so you have a single best model which is absolutely right. But in doing so, what you're doing is rejecting all of these other models, and some of these models might be very plausible. So for example, different models of natural mortality may also be plausible, and some of these can go on to give very different effects. In fact, as we saw yesterday with, I think it was Teresa's talk, where using a different natural mortality model inside an MSc gave quite a different set of results. So maybe rejecting all these other models isn't something we ought to be doing. So if we could change things, what might we like to do? For a start, I'd quite like to include some uncertainty on these biological parameters. Then I'd like to generate lots of different models with different underlying assumptions, run assessments in all of these models, but then somehow integrate all of these sort of results together to come up with a single sort of assessment with uncertainty. One of the problems we have is that all of this has to be timely, and I suspect that some of the problems that exist at the moment with the way that the European stock assessment system works is that the good people that are running these stock assessments are sort of locked in a room for a week, and they have to produce a vast number of stock assessments in a very limited period of time. So there's often not the time to go about exploring sort of new and exciting ways of doing things. So any sort of new approach that we're bringing here, this has to be sort of practically applicable so that it can sort of fit within the current framework. So with this in mind, what are we trying to do at the JRC? This is sort of what we call the A4A approach. A4A was originally in the title of the talk, but I took it out because it was a bit of a distraction. Very, very briefly, A4A stands for Assessment for All, which is a sort of an initiative that has been set up at the JRC. The idea being to develop sort of stock assessment techniques that can rapidly assess a large number of sort of data moderate stocks. So what I'm going to do for the sort of rest of the talk is talk through one of the case studies that we're working on at the moment, and which have sort of different uncertainties coming into a stock assessment. So the first little bit we look at is with the growth model. So we start introducing parameter uncertainty inside the growth model. We also look at the natural mortality model, where we start also introducing parameter uncertainty, but also what I call sort of model uncertainty, where in fact we start using two different natural mortality models. And sort of grouping these together, we can sort of call them biological uncertainty. We also have what I'd call stock assessment uncertainty. So we have sort of model uncertainty. This is different types of stock assessment model, or perhaps different settings within your stock assessment. And also uncertainty in the fit. So this is after you've run your stock assessment, you can look at how well the model actually fitted and sort of run simulations from the fit. Under the A4A approach, we've sort of developed some of the tools for each of these different components, and we've now sort of reached the stage where we're trying to try to combine them all into a sort of single cohesive idea, and that's what we're sort of hopefully going to show for the rest of the talk. Okay, so the case study, we're looking at Southern hake. We already had some hake today, so that's good. We were starting from sort of raw length-based data, so this is sort of the data which you initially get, so it hasn't been transformed particularly. We have a time series of catches at length, and we also have time series of 3 different surveys at length. We also have some other biological information, sort of estimated of maturation at length and mean weights at length and so on. So starting off, we'll look at the growth model. So first of all, why do we need a growth model? Well, the data we're using is length-based, as I said, but the stock assessment model that we're going to be using is age-based. So we need some way of converting from length-based to age-based data, and we're using the growth model to sort of slice it up to get the age-based data. As usual, we're going to be using a von Bertalanffy model, but you don't have to be restricted to using this. Other models are available. But what we want to do is put some variance on the parameters of the von Bertalanffy growth model. What we started off doing was, okay, the median value for the parameters, we'll just take those from the current stock assessment that was run last year. And to get some kind of idea of the variance in these parameters, we decided as a sort of first pass through it was to look at Fishbase. Now, initially I was concerned about using Fishbase, but after Wes's talk yesterday, I've been utterly convinced that Fishbase is 100% reliable, so it's perfect to use it. Rather than using sort of a normal distribution on these parameters, we decided to go for a triangular distribution. So we used the minimum and the maximum from Fishbase to set the minimum maximum of the triangle, and then the median value is obviously where the peak is going to be. L infinity and k we know sort of vary together, so for those we use a sort of a triangle copula to sort of describe a triangle sort of surface and how they vary together, which you can hopefully see in the plot a little bit there. And T0 we decided in fact wasn't going to be correlated with the other 2 parameters. It was still going to have a triangle distribution, but it was going to be a triangle on its own. It's going to be independent. And then we pulled 1,000 samples or iterations from these distributions to then parameterize this growth model. Oh, and that's sort of an example of what it looks like with length up the side and years along the bottom. So uncertain growth. Moving on to the natural mortality models, as I said, we started now to pick 2 different models. And the first one is sort of the standard one, which is used in the current stock assessment, which is we just assume it's 0.4 for all of the ages. But we've put a bit of variance on. You can see that in the top plot there. So we have some variance. Again, it's of a triangle. Is it a triangle? I think it was a triangle variance we put on it with limits on there. And the second model, sort of calling it exponential, where it's sort of declining with age, so natural mortality reduces with age. And this was based on some of the life history work that Henrik Gislason was doing. So that uses some of the parameters that are also used in the von Bertalanffy model. We also used, I think it's called Jensen's second estimator, which is a way of sort of scaling the natural mortality over an age range. Okay, as I said, it's got the same parameters as the growth model, so it also has the same parameter variance as was then used in the growth model. So the upshot of this is that we ended up with sort of 2 different stocks to be assessed, and the difference between them is that they each have a different natural mortality model. Both of the stocks have the same underlying growth model, and there's sort of 1,000 iterations or 1,000 samples from the parameter uncertainty underneath it all. Moving on to the actual stock assessment model, we're using the A4A assessment model, which I don't really want to go to in any great detail. But sort of very broadly, it's split into 3 different sub-models. The F model, which is for fishing mortality, the Q model, which is for catchability, and the R model, which is for recruitment. And for each of these sub-models, we sort of came up with 2 options. One of which was that F varies with age and it varies with year. The second option being it's a tensor spline, which then sort of varies smoothly over age and year. For the Q model, we said that catchability only varies with age, so it's constant through time. And the second option was that it sort of varied with age, but it also varied through the years as well. And finally, for the recruitment model, we said that recruitment sort of just changes with the year, but also the other option was to have a Bevered and Holt going on there. So with 2 options each for the 3 submodels, that gave us a total of 8 different stock assessment models that could be used. So what did we do with all of this? Well, we fitted each of the two stocks, which are differentiated by the natural mortality model, with each of the 8 stock assessment models. This meant that, of course, we had sort of 16 sort of different stock assessments being run, but each of those, of course, has 1,000 iterations in the parameter uncertainty going on behind it, and we fitted all of them. So we ended up fitting 16,000 sort of different stock assessments. Now, if you remember at the beginning of the talk, I said it was important that any sort of new approach had to be timely, and here we are fitting 16,000 of these stock assessments. It wasn't too bad. It sort of basically ran overnight with a multi-core computer, which is sort of a bit heartened by Santi saying it took 25 days for his model today, and it didn't converge then. So we're doing okay, but there's obviously still room for improvement. For each of the fits that came out, we then simulated from the goodness of the fit to generate new abundance and fishing mortality estimates. And the reason we were doing this is because we felt it was a way of combining not just the uncertainty in the growth in the M models, but it combined it with the fitting uncertainty from the stock assessment as well. We found that 2 of the stock assessment model combinations didn't work particularly well, so they didn't fit a lot of the time, so we discarded those. But this still gave us sort of 12 sets of results, where each set sort of contains the different model uncertainties, but each set has still 1,000 iterations, which now is a combination of the parameter and the fitting uncertainty. And yeah, we had 12 sets of results. I didn't want to put all of them up, but here's just an example of 3 of them. So the solid black line is this is SSB. I should clarify. Just quickly summarize it. This is how SSB. The estimated SSB was going through time. So the black line is the median value, and the 2 dashed lines are the 10% and 90% quantile. Something a little bit strange happening on the left-hand plot, where the median is so close to that sort of lower quantile, so we need to look at that. The AIC, which is written in quite small text, maybe you can't see, that's the AIC of the iteration which has the lowest AIC. So out of the 1,000 iterations, we found the one which sort of had the minimum AIC. We're using that as a kind of a proxy for the AIC for that whole set. So having generated sort of these 12 sets of results, what we wanted to do was sort of put them all together to come up with a single set, a single stock assessment with all of the uncertainty. And so we needed some way of sort of sampling from each of the different sets to sort of build up our final set. So how do we go about doing that? There's lots of different ways of doing that. You need to sort of give some weights to each of the sets that tell you how frequently you need to sample from them when you're building up your final set. Lots of different ways of doing this. I mean, Samu was talking about using sort of Bayesian model averaging yesterday, and that's something we certainly do need to look at. But just to keep things very simple to start off with, we use sort of a frequentist weights method, one that's called smooth AIC, developed by Buckland et al. In '97. And this basically uses the AIC to come up with the different weights for each of the model sets. What we found, though, is that this tended to be dominated by just one model. So if I go back to the previous slide, the one on the left, which has the AIC of was about 80, this set has the lowest AIC, and we found that even though there were other sets that had AICs that were similar to it, it didn't matter. 99.9% of the weight was dumped on this one set. So even though we were trying to do sort of some model averaging, it was basically averaging over just one model, so it wasn't particularly helpful. So as a sort of quick alternative, just to demonstrate a little bit of contrast in the results, so another way of doing it is you can try to incorporate some expert knowledge. We didn't really have time to do that, so as a quick example, I just sort of put equal weights to each of the models and then just sort of sampled from those to build it up. And so we can see the sort of difference that makes in that plot there, where the equal weights sort of in blue, and sort of the final set with the smooth AIC method is in the black. That's unfortunately as far as we've come so far with our results. We're still sort of picking through them and trying to work out the sort of different methods and trying out the different methods to put all these results together. But as a sort of a brief conclusion, sort of what we are trying to do is include all the different biological uncertainty in both the models and in the parameters behind these models, And we're also looking at including stock assessment uncertainty, not just in sort of the type of model we're using, but also with the actual quality of the fit that comes out of the stock assessment. As I mentioned, there's a whole range of different model averaging techniques available. We just started off by using a very simple one, but there's sort of different Bayesian ones that are available. Colin, one of the co-authors, has a food for thought paper out in the IC's journal earlier this year, which sort of summarizes some of the differences between them. But sort of the main approach that we're trying to come up with is trying to define the stock assessment as really as a set of models, and to try to move away from the idea of having just a single best model. I mean, some of the drawbacks of that are sort of well known, that you end up with sort of narrow confidence intervals, perhaps overly optimistic tests of significance, and perhaps some biased results. And what we're really interested in knowing is how including all this different types of uncertainty changes our perspective of the stock. So the next step is going to be sort of looking at how perhaps the reference points changes and how your status compared to the reference point changes, and so on. But we haven't got that far yet, but we'll let you know when we do. And that's it. Thanks.